Hello, everyone, and thank you for joining our webinar on the RDR-4000 no-fault found reduction. The RDR-4000 is a latest generation of the Honeywell Weather Radar Systems, which has a history going back for air transport as early as 1963. And the RDR-4000 system is the latest generation. And it is a solid state radar system, meaning that there is no magnetron tube involved. And some other technology benefits are that it contains what we call a three-dimensional or 3D buffer memory, which constantly stores weather radar data from 0 feet to 60,000 feet in altitude, and also from 0 nautical miles to 320 nautical miles in front of the aircraft at all times. And the way that works, the pilot and the first officer with their range controls can select and filter exactly what portion of that data they want to see at any time, but it's always processed, all that data at all times, and updated. The system is capable, of course, of weather operation as far as reflectivity off of rain droplets in clouds. It's also capable of Doppler turbulence detection associated with rainfall and predictive wind shear microburst detection. Depending on the software level that you have, there's a software level we call version 2, and you may also have the capability of hail and lightning detection, and also react mode, which helps to warn the flight crews about possible radar shadowing. The radar system, of course, increases the flight crew's situational awareness by detecting and enunciating weather conditions that can compromise the continued safe and landing capabilities of the aircraft. I also want to mention that this is an avoidance radar system, as historically these radar systems are. It's not designed for penetration. Major components in the system. It contains an RP1 radar processor unit, a TR1 transmitter unit, a DA1 antenna drive unit, and a CP1 control panel. The objective of this course is that we have observed, Honeywell's observed one or more unnecessary 4000 system component removals from aircraft based on some fault codes or fault code combinations, which have led to one or more confirmed component removals at our service facilities. This webinar and the associated service information letter that will be described later provides our airline operators and maintenance personnel with additional fault isolation and troubleshooting guidance, which uses the extensive byte capabilities of the weather radar's radar signal processor, which is located in the electronics bay, in order to help reduce the number of unnecessary removals, and which will help our customers reduce their operational costs and flight delays. This is a photograph of the front panel of the RP1 radar signal processor, which again is located in the pressurized electronics bay, which would be in the front E-bay on the 737, and that would be a single system. And in the Boeing 777, it's also in the electronics bay. You would have 2 of these units for a dual system. The LCD display is showing a fault code 3049 as an example. We'll be describing that shortly. You'll see 2 buttons just below the LCD display, and you use those to navigate through the display menus and through the fault codes. Then on the bottom left, you'll see a little door that's marked ATP. That is for a connection to either a laptop or computer, or mainly in our service shops, to the automated test equipment. And then on the right side, you'll see data load. There's a little window which is hiding a compact flash card slot, And many of our service bulletins for software-only upgrades, where no hardware upgrade is needed, you can actually update the software on this unit on wing. This is a picture of the TR1, the transmitter receiver unit. The TR1 is mounted in the bottom of the pedestal of the DA1 antenna drive unit, which is mounted on the bulkhead inside the radome of the aircraft. And in a single system, you would have one of these units, and in a dual system, two of these units. You'll see two large connectors, or well, you'll see a smaller and a larger connector towards the bottom of the unit. The smaller connector at the top, that connects to a cable which is part of the DA1 assembly, and that communicates to what I'll be describing as the gimbal drive module, the electronics in the antenna. The bottom large connector, and inside you'll notice two little coaxial connectors we'll be discussing. That is a large cable bundle that goes to the electronics bay and connects to the RP1 radar processor unit. And please remember these two little connectors, because we're going to be talking about two coaxial cables, one called the 64 megahertz clock cable and one the 48 megahertz intermediate frequency cable, sending data to the RP processor. So these are the two little connections inside the connector. This is a picture of a DA1B, which is the antenna drive unit for a dual system, such as what is installed on a Boeing 777. And you'll notice there's an arrow on the left side, a red arrow pointing to a kind of a bronze or gold paneled cover. Inside that cover is either one or two what are called GDMs, gimbal drive modules. And that is the electronics that drives the two motors, a azimuth motor and a elevation motor. If it's a dual system, you have two azimuth and two elevation motors. Unlike our previous systems, such as the RDR-4B system, there is absolutely no gearbox in this antenna drive unit. These are low RPM direct drive DC motors. And then for the positional information, they are directly linked to resolvers, which feed the positional information to the GDM module inside that casing, and then that's sent over to the RP1, which I'll be describing shortly. Down at the bottom, you'll see, again, since this is a dual system drive unit, the DA1B, you'll see two connecting cables. They are not removable. They're part of the assembly, and they connect to those smaller connectors at the top of the TR1 transmitter units, which slide and then lock in to the bottom of the pedestal in those cavities there on the lower right side. This is a schematic diagram showing, again, the DA1B like in a 777 dual system, and you can see the two TR1s, and then they slide into the cavities, and then they're locked in with captive screws, and then you have the two cables with the locking connectors connecting to the two small connectors on the top. Then coming from the RP1 in the E-bay, you'll have the two cables from the two radar processor units connecting to the two larger bottom connectors at the bottom of the TR1s. And then at the top of the schematic, you'll see the FP30, which is the 35 dB gain flat plate antenna, which is attached to the top of the drive unit. Waveguides, unlike the older radar system, which had a transmitter receiver and the radar processor in the E-bay, like the RTA-4B, all in one cabinet, and then there would be a long 10 to 15 meter waveguide all the way through the bulkhead and then into the radome. The only waveguide associated with this system is a very small waveguide, which is part of the DA1 assembly between the TR1 and then up to the flat plate. So it's only a a little over 1/2 meter in length. So we really reduced that problem by eliminating the long waveguide runs. This is an example for a aircraft that's a single system like the Boeing 737. This is a CP1A control panel. So in the looking at the controls, I have a left side for the pilot and a right side for the first officer. Notice that both of them independently can choose either the auto mode of operation for the weather, which is your normal mode of operation, or you can go to manual mode where you can select an elevation altitude of weather. For instance, if you're flying at 38,000 feet and you want to see, not in the automatic mode, but you want to see what the weather would be like at an altitude level of 18,000 feet, then you can go to the manual mode and then use the altitude control, which turns left and right, higher altitude by turning it clockwise, and manually select that to do a closer analysis of the particular storm that you'd like to look at. And like most previous radar systems, you do have a gain control. So both the pilot and the first officer have a gain. You normally leave it at the 12 o'clock position, which is the calibration position. And then you can turn it minimum or maximum. It has about minus 20 dB of gain in the minimum position and approximately plus 12 dB of positive gain in the maximum position. And again, you use this for along with the manual mode usually, or auto mode to better analyze the storms. And then at the top, there's a control, and you can see the same basic functioning on the dual control here. You have a test position and then the operational position. So this is an example for the dual system in a 777. The CP1B control panel, you have 2 tests which are exactly the same. It's just that one is for the left side and one is for the right side RP, just for convenience. But either will have the same test function. For instance, if you go from the right side and click it past left and go over to the full counterclockwise to test, it's going to be the same test if you went to the full clockwise test position. So this is how you select. Unlike the previous radar systems, you do not have a actual waveguide electromechanical switch. Inside the DA1B and a dual system like for the 777, in that assembly, there is a solid state driven waveguide switch, which is far more reliable than the older electromechanical types. So that is one of the functions of this switch, to switch that electronic solid state waveguide switch. And like the other panel, you still have the map, auto, and manual position. Sometimes the question comes up, what is the difference between the map mode and the auto and manual mode? I mean, obviously it's to look at ground terrain. And what we change in the map mode, we change what is called the sensitivity time curve or sensitivity time constant, how we process the weather. Because in the weather mode, we try to optimize the weather so that near storms have the same apparent strength as far storms, as far as, trying to equalize it so that you would see a constant display, an equalized display. But you cannot do that in the terrain mapping mode, because all your terrain would look flat and the same color. So you would not get the relief, the ground relief. So we changed the software in the map mode to better visualize the ground returns. This is a block diagram of is an example of a single system in a 737. So the heart of the system, of course, is the RP1 radar processor unit, again, mounted in the E-bay. There is a mounting tray. We have several configurations of trays. They can accept either forced air cooling from the aircraft blowers, or there's a dedicated electric fan. And technically, the RP1 radar processor can function without cooling, but we have it in the aircraft certified with either cooling fan or forced air cooling. as preventive maintenance. Maintenance. The RP1 receives 115 volts AC aircraft power, and the main power supplies for the entire system are located in the RP1. So talking about power, the RP1 takes the 115 volts AC and creates several various internal DC voltages for all of its processing circuitry. Then it provides a plus 200 volts DC level up to the TR1 inside the radome at the bottom of the DA1 antenna drive pedestal. Then the TR1 has a small internal power supply, which drops down the 200 volts DC and creates approximately 20 to 50 volts DC internally. And then it has the responsibility in its power supply to send plus 29 volts DC to the drive unit's GDM gimbal drive module in order to power it up. One of the reasons, sometimes a question will come up, why such a high voltage between the RP1 and the TR1, the plus 200 volts? And it's because we really don't want to provide a voltage like 28 volts DC at several amps. So if you have, much like the electric companies, if you have a much higher voltage and a lower current, you still have the same power, the wattage capability. And so it's just easier on the wiring to use a higher voltage with a lower current. And then later on, you can do a down conversion of the voltage and achieve your currents necessary at the same time. Okay, so that's voltage. Now we need to provide an interface between the RP1 radar processor unit and the other aircraft systems. So that's by means of discrete logic, which is either grounds or opens, or ground or 28 volts, or primarily we use ARINC-429 low speed and high speed data interfaces. And then the RP1 needs to communicate with the TR1 transmitter receiver unit. And we can do that in two ways. Number one, there's a bidirectional high-speed ARINC-429 interface. So when the radar processor sees that the circuit breaker's on and the power supplies have stabilized, and it does an internal self-check of its circuits, using ARINC-429, it will give the command to the TR1 to wake up and start functioning and check itself internally, do an internal self-test. Then it's the responsibility of the TR1 to use a RS-422 bidirectional communications circuit to the GDM module inside the antenna drive unit to tell it to wake up, do an internal self-check, and prepare for operation. Now, one of the things that we wanted to do is that the TR1 is going to be transmitting an output signal of 9336 to 9376 megahertz. So then that is sent from the transmitter portion of the TR1 through the waveguide section to the FP30 flat plate array, through the small waveguide section in the DA1. Then the return signals from the clouds are sent back in at very low signal levels, and then they're amplified and processed by the receiver, which is in the TR1. Then the TR1 does a down conversion of the 9 gigahertz radio frequency signal to a much more manageable lower frequency of 48 megahertz. So we call that our 48 megahertz IF. And then that's sent on a coaxial cable to the RP1, which will then do an analog to digital conversion, then a lot of digital signal processing magic inside, and then it will produce the video and audio outputs that you see in the flight deck. Now, in order to synchronize the two from a radio frequency point of view, we decided that the TR1's clocks, which produce the transmit and receive local oscillators internally, we would provide a sample of a 64 megahertz local oscillator, and we're going to send that signal to the RP1 through its own coaxial cable, and the RP1's internal radar processing circuitry we'll use that as the sampling clock in order to do the digital signal processing of the signal. Then, for communications purposes, we're going to use biphase shift keying modulation and modulate that 64 megahertz clock signal from the TR1. And that will be real-time data that the TR1 will inform the RP1 of the antenna's position, both the azimuth position and the elevation position of the antenna, the basic health status of the antenna, and also the basic health status of the TR1. It will confirm whether I'm in the weather mode, the manual mode, or the map mode, and also the pulse widths and pulse timings, so that if there was a major problem, the RP1 would know to shut it down for safety. So 2 communications, ARINC-429 and modulation of the 64 megahertz clock signal. And then lastly, on the left side, you have your control panel, and the control panel needs a power supply voltage. So the power supply in the RP1 supplies plus 28 volts to the CP1 in a 737 or possibly a CP2 control panel and a 777 for dual. And then the positional data of the controls, the gain controls, mode of operation, and the health, the byte of the control panel is sent by means of a single RS-422 data bus to the RP processor unit. And then I would like to mention 2 other things. First of all, when you have a service bulletin and you're going to need to reprogram the RP1 using a compact flash card, this is how it works. The RP1 would accept the data from the compact flash card, reprogram itself, then it will be told on instructions on the compact flash card to do a self-test internally and check everything, hardware and software. Next, once it knows that it's working correctly, it's the responsibility of the RP1 using the ARINC-429 bus. It will program the memory inside the TR1 to bring it up to the latest TR1 software level. And then using the ARINC-429 bus back to the RP1, the TR1 is to confirm bit by bit to the RP1 that the programming has been successful. Once the RP1 knows that the TR1 has been reprogrammed successfully, it will then give the TR1 a command to use the RS-422 communications to the GDM drive module in the antenna drive unit, and then it will load it with the new data. Then the GDM, after the data load, will confirm the success of the data load to the TR1, which will relay that successful data load back to the RP1, and then you can use your radar. It will be back to normal mode of operation. And then lastly is byte. The RP1, again, is the center of the byte, and it will give commands to the TR1 to say, hey, how are you feeling? And if you have any problems, I want you to relay any of your TR1 fault messages to me, and then I will store them in non-volatile fault memory, which we can see on the LCD on the front panel as byte codes that we'll be discussing shortly. Excuse me. And then also the DA1 has fault codes, and it will relay those fault codes to the TR1, and then the TR1 will relay those fault codes to the RP1, again for storage in the non-volatile fault memory. And that is your complete RDR-4000 system. Now a little bit of detail, and this will lead into the description of the fault codes that we would like to give you aid in helping to reduce unnecessary removal of RDR-4000 components, so we can help you remove the correct failed unit. Again, the RP1 receives the 115 volts from the aircraft, and we have the ARINC-429 and discrete logic interface with the aircraft, and you can see the various aircraft systems that we interface with. This radar talks, of course, much like TCAS and the EGPWS. So We send audio to the audio management unit so that we have the wind shear ahead, and monitor radar display messages, or the whooping siren as an alert. We have to communicate with the Enhanced Ground Prox Warning System, the EGPWS, to correlate and coordinate priority of both audio and visual announcements of events. The navigational displays, we still provide on Boeing aircraft ARINC 453 video to the display electronics units and the AIM systems or equivalent systems in the Boeing aircraft. We have to do coordination of alerts with the traffic collision avoidance system, the TCAS or ACAS systems. We, like all radar systems, we need attitude data. So we receive data from the ADRU, the Air Data Inertial Reference Unit, along with barometric altitude from the air data computer portion, as an example. Flight control units, those are from the display electronic units. They are the pilot and first officer navigational range control data for our displays of the radar data. Prediction wind shear qualifiers, when the system's in the gate area, we do not want to transmit for ground crew safety. So in the 737 and the 777, we usually monitor engine performance. And when we reach about 70–75% just prior to takeoff roll, if the system's in the off position, that's really the predictive wind shear standby position. And then just prior to the takeoff roll, will enable wind shear if the pilot has not turned on the system. Central maintenance computer, of course, that would only apply to the Boeing 777. We interface with that. This system, in the auto mode, we produce what is called primary and secondary or relevant or irrelevant weather based on the aircraft's flight path and also our flight altitude. So we need data from the flight management systems. And then, much like ground prox and TCAS systems, there are certain altitude trip levels for performance of the system on takeoff and landing. So we need inputs from the radio altimeter. And now Rosemary is going to start a discussion on the bite.
Troubleshooting. A 3049 fault usually gets logged when the estimated received power is very low for each pulse, and the pulse sequence is probably less than 8 seconds or so. And when this fault occurs, the radar processor IF converter logs receive power bit test fault. Similarly, a 3057 is a weather radar RP receive power fault, which is reported by RP IF converter. Now, when both of these faults get logged, we have noted that the transmitter receiver has been replaced, which is mostly tested, no fault found at Honeywell RNO. And we suspect that the RP would be the primary failure, and we recommend the replacement of RP for these two fault codes. Only if the fault continues, then we recommend to check the continuity of 48 megahertz IF coax cable from TR to RP. Now, for the combination of faults that you see below, a 3055 and 3716 getting logged together, we've again noted that there have been TR removals for when these two fault codes are logged together, mainly because a 3055 would indicate a PWS INOP and a WXR INOP in the cockpit. But for these two fault codes as well, we recommend the RP to be removed. A 3055 will get logged when digital receive processor detects the formatted pulse data message inactivity fault. That is, when there is no pulse data message received for 2 seconds and the radar is in transmit mode, then this fault usually gets logged. And the 3716 would be logged when RDSP visual ARINC 429 antenna status bus fails in monitor state. And this fault would also log a Vixor NOP and a PWS NOP when the antenna status bus is inactive. So for all of these fault codes, the first troubleshooting would be to replace the RP, and then would follow the next troubleshooting. Now we're moving to the control panel faults.
So again, the CP1 or CP2 for the 737 or the 777, we received 28 volts from the RP1. Then the control panel sends health data using RS-422 to the RP1. And then finally, the control positions, mode, gain, etc., are transmitted that positional information via the RS-422 data bus to the RP1.
Right. The control panel has two faults, 8001 and 3106. The 8001 fault gets logged due to control panel internal failure, and it could be a combination of all of the detectable control panel faults. And if there is a hard failure of 8001, then the control panel would have failed and not the RP. And we recommend the first troubleshooting is to check the control panel functioning and replace if necessary. Now, a 3106 fault occurs when the control input, operational or display selection of the captain and first officer show a mismatch in data. And this fault could also get logged if an unassigned mode is activated. If only 3106 fault is logged, then none of the RDR-4000 components need to be removed, as it could occur anytime during normal operation, and only if a 3106 is logged with an 8001 fault, then we recommend the control panel to be removed and most likely being faulty. We're moving to the TR faults now.
The TR1 and the RP1 interface again. The RP1 supplies plus 200 volts bias to the TR1. And then there's the communications, ARINC 429 bidirectional high-speed buses between the two units. And then there's a secondary communications, which is biphase shift keying data, which rides the 64 megahertz clock bus. Please remember this, the other purpose of the 64 megahertz is a synchronizing clock for the radar signal processing inside the RP1. And then finally, the TR1 does a down conversion of the 9.3 gigahertz received signal to a much more manageable 48 megahertz VHF IF through the coaxial cable.
Yeah, and we saw earlier that a 3055 fault getting logged was due to formatted pulse data message received for 2 seconds when the radar was in transmit mode. And when a 3055 is logged with the 3716, then it's RP faulty. But in this case, we say that only if a 3055 is logged, then it would be most likely a TR faulty and not the RP. A 5051 and 5046 are TR down converter failures. 5051 fault is declared when the down converter is in calibration mode and the pin state is low. And this indicates that the IF calibration is out of specified limits. And when in receive mode, uh, a 5046 could get logged if the pin state is also in low, indicating a failure of local oscillator on down converter. Now, both of these fault codes clearly indicate that the TR has failed and not the RP. So the only troubleshooting step here is to replace the TR. The 4001 fault is, well, this is actually used to verify a switching device if it's open or short on the DA motor drive, and most likely a TR faulty and not because of a DA. Only if the TR replacement does not clear the fault, then the DA is recommended to be replaced. Coming to 4015, which is a TR 422 activity check. This fault is to check the RS422 activity from TR to DA and could occur anytime during cycling of 200 volts to DA. This again is leading to a TR failure, and the second troubleshooting step would be with DA. Now 3049 and 5051 logged together in the same flight leg. We saw earlier that if only a 3049 is logged, then the RP has failed. And if only a 5051 is logged, then the TR has failed. But when both of these faults are logged together in the same flight leg, then we can be for sure that the transmitter receiver has failed, and we recommend a TR replacement. Similarly, a 3057 and a 5051. A 3057 would cause an RP failure, and a 5051 would be a TR failure. But when a combination of these two faults are seen in the same flight leg, then it's most likely the TR being faulty. We're now moving to our question.
Yeah. Okay. Yeah. This is a good place to take a few questions here while we digest a little bit of what you've given us so far. If you have any questions you'd like to ask at this point, move your mouse along the bottom of your screen, and you'll see the Q&A tab. Go ahead and click on that, and then you can type your question in text. One of the things I've been wondering, Bob or Rosemary, whoever would like to answer this, you're talking about two codes at the same time, like the 3049 and the 5051, if those appear. What's that look like on the RP1? Is there enough screen space available on the display where you would actually see both codes at the same time? Or do you have to scroll through the fault history to find them? How does that work?
Yeah, so as explained earlier, these faults, you have to scroll down. So in each leg of flight leg, you would see multiple faults logged sometimes. So you have to scroll down to capture these fault codes.
Okay.
Take a note of them and guide with troubleshooting, yeah.
Okay.
And the instructions for doing so are located in the Honeywell line maintenance manual for the Boeing aircraft or generic federated aircraft, and then the reference section at the end will give you that document number. It's in the troubleshooting section.
Okay.
The process.
Okay. Well, that's we don't have any questions just yet. Nobody's submitted any. So let's go ahead and jump onto the next topic, which is going to deal with the DA1AB fault codes.
Okay, in this section, this is the interface, as you mentioned, between the TR1 and the DA1A and a 737, or DA1B and a dual system for a 777. So again, the TR1 has the responsibility to supply plus 29 volts DC bias to the GDM module and the antenna drive. And then both command communications and health communications and status communications between the TR1 and the DA1 are by means of a bidirectional RS-422 communications buses. And then there's the waveguide section, which is used for both transmit and receive, of course. So the TR1 supplies the RF energy to the small waveguide section inside the DA1 antenna assembly, and then that is routed through to the flat plate. And if it is a dual system, DA1B, there is a waveguide switch connected to a small section of waveguide to the flat plate, And then there are actually two small sections of waveguides from each TR1. There are two of them in the bottom of the pedestal. And then there's a solid state waveguide switch controlled by the CP1 or CP2 control panel through the RP1, through the TR1, back to the DA1 solid state switch, selecting either position 1 or position 2.
Right, and most of you would be aware of spurious or nuisance occurrences of radar byte fault 5049. We have also published a SIL describing this fault code and recommending customer action. And this fault could get generated during power transients like those associated from transition of aircraft to ground power and engine shutdown. And during these power transitions, there could be a temporary loss of RS-422 data communication between the receiver transmitter and the antenna drive, which may result in a WIX or NOP condition and logging a 5049 fault. Uh, this fault generally persists for approximately a minute before clearing by itself through reset. And some of the operators remove the RTU suspecting a failure, but we recommend the operators to perform a self-test to continue, and only if the 5049 fault code continues, then we recommend replacement of DA.
Okay, in our next section, we're going to concentrate on the 64 megahertz clock cable. And I do want to talk about we've already mentioned that it's a synchronizing clock for the RP1 and also a data communications using the BPSK data. But now is a good time to mention troubleshooting of both the 64 megahertz and the 40 megahertz cable. If per the fault codes, there's a suspicion about a problem with one or both cables. Of course, the coaxial cables, even though these are VHF frequencies and not microwave, you really can't troubleshoot it visually that well, or also by using a means of resistance checks, using an ohm meter. The best means of checking these cables is by the use of a TDR, a time domain reflectometer. And with that tool, you can actually determine if there's an open or short circuit and exactly how far away from the source, which means where you've injected the signal, let's say at the RP end, you can determine where the problem might be. And of course, as far as repair, unless there's in the Boeing AMM, there is a procedure for replacing connectors on the cable. Usually it just means replacing the coaxial cables themselves, if the TDR confirms a problem.
Yeah, and the 3042 is the RP pulse data message communication fault. And when this fault occurs, we recommend to first check the continuity and condition of 64 megahertz clock cable to check if the wiring is satisfactory, and only then replace the TR as the second troubleshooting step. If the fault continues, then the RP could also be faulty in logging this fault. We saw previously that only if a 3055 is logged, then the TR is faulty, and only if a 3057 is logged, then RP is faulty. There is a possibility for both of these fault codes occurring together, now which clearly indicates a 64 megahertz cable connectivity issue. And the first action would be to inspect, and if required, replace a 64 megahertz clock cable. Only if the fault continues even after cable replacement, then we recommend to replace TR. We usually see for these two fault codes logging together that customers replace both RP and TR together, wherein it would lead to no fault found of both these components. And we're moving to the next.
Okay, just before we go on, we do have a couple of questions that have come in, and I just want to let people know that we will be getting to those questions in a few minutes. So please stand by, and we'll get to you.
Okay, this is the interface between the TR1 and the RP1, again with the ARINC-429. Again, these are dual 429 high-speed buses, 100 kilohertz each. And these are the related fault codes for those two cables.
Yeah, we saw initially that 3716 getting logged would be an RDSP visual at ARINC 429 antenna status bus fault. And when antenna status bus is inactive, a weather inop and a PWS inop also would get logged with RP showing as 3716. But this is with a combination of 3055. But only if the 3716 fault code gets logged, then we suspect that the ARINC 429 data cable is faulty. And we recommend replacing this cable if necessary. And the second troubleshooting step would be to check the TR. A 3029 is a weather RDSP, digital receiver FPGA. It's a single event upset fault. And this fault is logged when FIFO status error bit indicates a single event upset. This again is likely an ARINC 429 data cable fault. And a 3032 is logged if could be logged if there are errors with serial communication status like receiver overflow or receiver sync error or transmitter sync error, etc. And this fault could lead to a reset of the main processor. And if this fault exists, then we recommend to check and replace the ARINC 429 cable as the first troubleshooting step. And the second would be to replace the RP. With this, we come to an end of BY troubleshooting guidance for NFF reduction.
And to summarize, this webinar has presented a more clearly defined cause and suggestive actions for the key fault codes observed on the RP1 radar processor, which should help you to lead to correct first removals of failed RDR-4000 system components. And with that, it will lead to fewer unnecessary removals, which should help reduce your operational costs and flight delays. There is the mentioned service information letter, and it's in our technical publications website. We'll be giving you that information at the end of the webinar, and that gives additional details. And there's also the related line maintenance or installation manual for the system, and we'll be giving that number, the documentation number at the end as well. We've updated all the byte operational code tables in the troubleshooting section, and it also gives extremely good operational theory background at a system level, and any needed information as far as the individual components and mounting suggestions and routine maintenance. And these are the document numbers. So the installation design guide and line maintenance manual. This was our original manual for what we call our federated system, our generic system, and for the Boeing aircraft in particular. And the document number 01207451, that's available on our technical publications website. And related to this webinar, the information taken from it is the service information letter. And again, that's available on our TechPub's website.